Hi everyone. Today I'm just going to pretty much go over parts of section one. So as you were told in class, you're responsible for pretty much reading sections one and two, but there's a few things from section one that I wanted to highlight. As far as section one goes, we are talking about representing functions. As mentioned, for the most part, you are responsible for reading this section. And like I said, most of the stuff that you've dealt with here is more or less review. There's nothing that's out of the ordinary as far as what you saw in analysis. However, there's a few important topics here that I want to kind of touch up on and talk about the importance of them, especially in this class. So the first thing I want to talk about is the absolute value. So as you've as you remember from previous years, the absolute value is described as the distance from the origin to a certain point, and therefore absolute value is always a positive number. Okay, and so just to give you the formal definition of the absolute value, the way we can state it is that the absolute value of a number a is the distance from 0 to a. Okay, and so that's basically nothing new here for us. However, what I'd like to point out is the absolute value also could be treated like a piecewise function, and that's very important in calculus because almost anything we do, whether it's graphing absolute value functions, which there are some pretty complicated looking absolute value functions that you'll come across in the homework, or if it's dealing with limits, we always want to kind of get rid of the absolute value. And when I say getting rid of the absolute value, we're translating it to like a piecewise function. What we could also say here is that we have um, the absolute value of a equals to a if a is greater than or equal to 0. So in other words, what we're saying is, look, if the absolute value of a, or if a itself is a number equal to or greater than 0, we can just get rid of the absolute value because it is already pretty much positive. So there is nothing we need to do to it. However, if we have something like in the form of if a is less than 0. So now the question is, if a is less than 0 itself, can I just get rid of the absolute values? And obviously we can't, because if a is greater than 0 and I get rid of the absolute values, then I'm claiming that this absolute value is a negative number. So what adjustments do I need to make? In other words, if I'm removing the absolute values, what do I need to tack onto a where I'll force it to be a positive number? And the answer is you put an extra negative in front of it. So think of it this way. Since a is a negative number, if I take the opposite of a negative number, I get positive. So in other words, if you notice, I pretty much created a piecewise function for this absolute value. So in other words, we just showed, or maybe I shouldn't say words, it's more or less symbols, but we have the absolute value of a is equal to a and negative a. That's if a is greater than or equal to 0, and that's if a is less than 0. Okay. Now, just to point something out, as far as the equality goes, it doesn't matter to which one I give it to. I could give it to this one or this one, because if a itself is 0, then whether you call it 0 or negative 0, it's the same thing, because 0 is not positive, nor is it negative. Okay. But what's important is whenever we have an absolute value, we want to think of it as a piecewise function, especially in calculus. And you'll see how that allows us to simplify things. We're usually stuck. We don't know how to simplify these unless I could somehow get rid of the absolute value. So the best way to get rid of the absolute value is to treat it or convert it to a piecewise function. Okay, so the next thing I want to talk about, which you pretty much saw in pre-calculus quite a bit as well, are even and odd functions. Okay, so I'm pretty sure you're familiar with this. So what could we say here? A function is an even function if f of negative x equals to f of x. Okay, and so that's basically what an even function is. And so what we could say is, by definition, since this is an even function, we could say that all even functions are symmetric with respect to, and by the way, you'll probably see this notation quite a bit, and it's common in mathematics. So instead of writing with respect to, we just call it WRT. So that's all we're saying. We're just trying to shorten it. We're mathematicians. We're pretty lazy when we need to be. So it's pretty common. So when you see WRT, we're talking about with respect to the y-axis. Okay, and so this is clear why we can say that even functions are symmetric with respect to the y-axis, because what am I claiming here? If you look at this, I'm saying when my x values are exact opposites, my y values are still the same. So visually speaking, here's what we're claiming. See, if this is x and this is negative x, and the y value at negative x, let's just label it this point. What would this be? This would be f of negative x. Okay, so that's f of negative x. That's the y value. But however, what is it that we're claiming? The y value at x is also the same thing as the y value at f of negative x. So what we notice here is that the y value at x and the y value at negative x, they're both the same, and that's why you get that symmetry with respect to the y-axis. Okay, and so that's why, by definition, this is an even function, which also becomes symmetric with respect to the y-axis. Okay, so moving on to an odd function. So what we could say here is that a function is an odd function if f of negative x equals to negative f of x. Okay, so once again, what does this say? If I replace x with negative x, I get the exact opposite of the original function. Okay, and so basically what we could say is that all odd functions are symmetric. So all odd functions are symmetric with respect to the origin. Okay, so basically the way we check to see if a function is even or odd, you grab the original function, you replace x with negative x, and then if you get the same function as the original function, it's even. If you get the exact opposite function of the original function, after you simplify it, it's an odd function. Okay, so let's just do a quick example, and this example you guys should be able to do on your own. So maybe you'd want to pause this video as I put this example up, work on it on your own, and then look at the solution yourself, or you can just go ahead and just work through it with me. So determine if the following function is odd, even, or neither. So the function is f of x equals to 3x cubed plus 2x minus 1. So what I want to do here is to check to see if this is even or odd. I grab x and I replace it with negative x. So the solution here is going to be replace x with negative x. And what do we get? So that means go to the original function. Everywhere you see an x, replace it with negative x, which gives us 3 negative x quantity cubed plus 2 times negative x minus 1. So this becomes, once I simplify it, negative x cubed is negative 3x cubed, and 2 times negative x is minus 2x minus 1. Okay, and so now here's where, once I completely simplify this, I start comparing this to the original function right here. So now the question is this exactly the same as the original function? Now, obviously it's not, because I have positive 3x cubed, negative 3x cubed. So as it is, these two are opposites. So now my next question is, are these two functions exact opposites? If they are, then the answer is it's an odd function. So let's see, 3x cubed, negative 3x cubed. So far they're opposites. Negative 2x, positive 2x. So far they're opposites. However, we have negative 1 and a negative 1. So these are actually the same. So this is actually not equal to f of x, nor is it equal to negative f of x. This isn't the same as that, nor is it the exact opposite of that. So what that means is that this is neither. Okay, so the last thing I want to talk about is, and this is for the most part has to do with notation and the way certain things are defined, which I think is kind of crucial, because sometimes you might see some way something is described and it really makes no sense until you kind of sit there and kind of look through it, and then it'll make sense. So this has to do with functions that are increasing and decreasing functions. Okay, so let's define what a function is increasing. And like I said, the notation here, or the way it's described, might be a little weird to you, but don't worry, we'll go over it. And then the decreasing definition will pretty much be trivial. So here's what we say. A function f is increasing on an interval I if f of x sub 1 is less than f of x sub 2 whenever x sub 1 is less than x sub 2. Okay, so we'll kind of talk about this visually, and it'll make sense to us as to once we see a picture. Usually, at least for me, I'm a very visual learner, so once I see something that's a picture that describes the words, it's very easy for me to make the connection. So hopefully it'll do the same for you. So here's what we have. This is saying, look, a function is increasing on an interval I. So, and by the way, we always describe where functions are increasing and decreasing through intervals, which is through their x values. So for example, if I have a function that looks like this, what do I notice? This function is actually increasing from that x value, which let's call it x equals a, all the way to this x value, and let's call that x value b. So notice how I would say that this function is increasing from where? From a all the way to b. So that's what they mean by an interval. So you never ever describe a function where it's increasing, decreasing through its y values. You describe it through its x values. So if I say a function is increasing from a to b, then if you go from x equals a and you move all the way to the right, you should see that the function should be increasing all the way until you get to x equals b. Okay, now here's what they mean by this x sub 1 and x sub 2. So we know that this function is increasing between a and b, and we know that for a fact. So what this definition is saying is, look, if you pick any two x values in that interval, and and by the way this has been defined is, call the smaller of the two x values x sub 1. So by definition, we're going to call this x sub 1 and x sub 2. And what they're saying is, look, if this is truly increasing, then the y value at x sub 1 should be less than the y value at x sub 2. Now look at what happens here. That's the y value right there. at x sub 1. And then that's the y value at x sub 2. And what do we notice here? The y value at x sub 1 is less than the y value at x sub 2, which makes sense because if this function is increasing, when I move to the right, the function should be going upwards, which means its y value is increasing. So that's what this means. A function is increasing if the y value at x sub 1 is less than the y value at x sub 2, given that x sub 1 is to the left of x sub 2. And that's basically what it means to be increasing, or in this case, increasing. So as far as decreasing functions go, they're the same thing. Okay, so that really doesn't change much. So if I'm talking about decreasing, we could say a function f is decreasing on an interval I if f of x sub 1 is greater than f of x sub 2 whenever x sub 1 is less than x sub 2. So now this one, if you look at this, the definition is fairly similar. However, the inequalities have switched. So which makes sense because look, if a function is decreasing, as I move to the right, it's going to go downward, right? So what you notice is this. If this is x sub 1 and x sub 2, clearly, as I move to the right, my y values are dropping. So what is it that we're saying? If x sub 1 is to the left of x sub 2, then the y value at x sub 1 should be larger than the y value at x sub 2, and that's what it means for a function to be decreasing. Okay, so that's kind of like what this definition here means. Okay, so that pretty much wraps up what I wanted to highlight from section 1. Please make sure to read all of section 1. Like I said, none of it should be things you haven't seen. You've seen it before, but you should still read it to just refresh your memory. Okay, so I'll see you tomorrow.